Alright guys, so today we are going to talk about the ratio and root test, that 9.6, okay? Now, the ratio test, okay, says this. Let the series be one with non-zero terms, okay? And why is that? Because the ratio test involves finding the limit as n goes to infinity of absolute value of an plus 1 over an. The denominator can't be 0, that's why we are saying it should not have any 0 terms. It should have all non-zero terms. Okay. All these three conditions will be given to you on the test on a chart. Okay, so you don't have to remember the conditions. So let the series be one with non-zero terms. The series converges absolutely when this limit as n goes to infinity, absolute value of an plus 1 over an is less than 1. The series diverges when that limit is greater than 1 or when that limit is equal to infinity. Unfortunately, guys, the ratio test is inconclusive when the limit as n goes to infinity of the absolute value of an plus 1 is exactly equal to 1. In that case, of course, you have to do another test, okay? Have a look at this. Determine the convergence or divergence of this. You may remember I mentioned that when n factorials are involved, the best test to test for divergence or convergence of the series is the ratio test, okay? So have a look, guys. Here, an is 2 to the power n over n factorial. An plus 1 is going to be 2 to the power n plus 1 over n plus 1 factorial. Okay, to determine the convergence or divergence of the ratio test, you have to find the limit as n goes to infinity of the absolute value of an plus 1 over an. That is the limit as n goes to infinity of an plus 1, 2 to the power n plus 1 over n plus 1 factorial, divide by an, flip it, that's n factorial over 2 to the power n. As you may remember, earlier on in 9.1 we spent some time simplifying factorials. I hope you can simplify this without much difficulty. Okay, so 2 to the power n divided, 2 to the power n plus 1 divided by 2 to the n is actually 2, right? Because you have an extra 2. Guys, when it comes to factorials, write the larger factorial using the smaller factorial. So I'm going to write n plus 1 factorial as n factorial times n plus 1. Remember how we simplified factorials back in 9.1? If you have forgotten how to simplify the ratio of factorials, please go back to 9.1 and have a look at it. Okay, n plus 1 factorial is n factorial times n plus 1. N factorials cancel out. This is going to be limit as n goes to infinity of, now absolute value of 2 over n plus 1 is simply 2 over n plus 1, guys, because n is a positive number, and that limit is 0. And the ratio test says if the limit is less than 1, the series converges absolutely. So let me go back up here and write the original series n equals 0 to infinity. 2 to the n over n factorial converges absolutely by the ratio test. Okay? Are you wondering how we were able to determine absolute convergence? Remember, guys, here the condition says the series converges absolutely when the limit of the absolute value of the ratio is less than 1. And that's why we are able to do absolute convergence, because we are taking the limit of absolute values. Okay, guys, so identify your an, figure out your an plus 1 by increasing n by 1. Everywhere you see an n, increase it by 1. Find the limit as n goes to infinity of the absolute value of an plus 1 over an, and if that limit is less than 1, then the series converges absolutely by the ratio test. Alright, determine the convergence or divergence of this series. Let's try and apply the ratio test, okay? First of all, guys, this is not geometric. This can't be put in telescoping form. This is not a p-series, and it's not easily integrable. Nth term test for divergence might be a little tricky on this, so let's go ahead with ratio test. So an is n squared 2 to the power n plus 1 over 3 to the n. Okay, what's an plus 1? Go ahead and replace all the n's by n plus 1. N plus 1 plus 1 would be n plus 2. 3 to the power n plus 1. Okay, get ready to find the limit as n goes to infinity of the absolute value of an plus 1 over an. That is limit as n goes to infinity of, what are we going to have? Put your an plus 1 first. You are dividing by an, guys. Be sure to flip the fraction and multiply. Now go ahead and find this limit. Okay, limit as n goes to infinity of look, what's going to happen? I'll keep my n plus 1 squared. Okay, now this is 2 to the power n plus 2. This is 2 to the power n plus 1. We have an extra 2 in the numerator. Okay, now look, this is 3 to the power n. This is 3 to the power n plus 1. We have an extra 3 in the denominator. What else do we have? Remember, guys, we also have the n squared. Okay, now n plus 1 squared times 2 times 1 over 3 times n squared. They are all multiplied, right? So the constant can come out of the absolute value sign. So we can pull the 2/3 out. Limit as n goes to infinity of n plus 1 squared over n squared. What is that limit? Both the numerator and denominator have the same power. So that limit is going to be 1 multiplied by the 2/3 outside is going to be 2/3, which is less than 1. That is great. So we can say the original series converges absolutely by the ratio test. Okay, guys, every time you do a conclusion, you have to name the test. Okay? Next question. Determine the convergence or divergence of this. Okay? N factorial is involved. Let's go ahead with ratio test. an is n to the power n over n factorial. An plus 1 is n plus 1 to the power n plus 1 over n plus 1 factorial. Okay, so you want to find the limit as n goes to infinity of absolute value of an plus 1 over an, right? That is limit as n goes to infinity of, what's an plus 1? N plus 1 to the power n plus 1 over n plus 1 factorial. And you're dividing by an. Flip and multiply. That's going to be n factorial over n to the power n. Limit as n goes to infinity of, how do we simplify this? Remember, guys, rewrite larger factorials using smaller factorials. Okay, so let me keep this as n plus 1 to the power n plus 1. Let me go ahead and rewrite this larger factorial using the smaller factorial there. What is n plus 1 factorial? Isn't that n factorial times n plus 1? It is important you rewrite it. Okay, so limit as n goes to infinity, n factorials cancel. Now look, we have n plus 1 here, we have n plus 1 here. Its power is n plus 1, its power is 1. So don't you think when they cancel, you are going to have an n plus 1 raised to the power n? In the denominator we have n to the power n, which we can write as limit as n goes to infinity of n plus 1 over n raised to the power n. What is that limit? Of course, the limit of the parentheses is 1, but this is infinity. 1 to the power infinity is an indeterminate form. We covered this particular limit back in section 8.8 when we did L'Hopital's rule. It's a long procedure for a question that is of 1 to the power infinity indeterminate form. We have to take ln both sides and go ahead and find the limit. Guys, the result of that limit is e. Please go back to chapter 8, section 8.8. The limit of this is e, which is greater than 1. What does the ratio test tell you if the limit is greater than 1? Ratio test tells you the series, the original series, n to the power n over n factorial, diverges. Let's name the test, guys, by the ratio test. Got it? Guys, if you're still wondering about the limit e, go back to section 8.8 and have a look at how we computed the limit. Okay, it is one of the several indeterminate forms that we covered. Alright guys, a failure of the ratio test. When does the ratio test fail, guys? Ratio test fails when the limit is exactly equal to 1. In that case, of course, we have to apply a different test, okay? Let me show you why this fails. What is an? Negative 1 to the n, root n over n plus 1. What is an plus 1? Negative 1 to the n plus 1, right? Increase all the n's by 1, square root of n plus 1 over n plus 2. Okay? Talk about the limit. Limit as n goes to infinity of an plus 1 over an. Okay, what is that limit? What is an plus 1? That's negative 1 to the power n plus 1, root of n plus 1 over n plus 2 divided by an, flip it, and multiply. So that's what you have. How do we simplify this, right? Now look, negative 1 to the power n plus 1, negative 1 to the n. You have an extra negative in the numerator, and that's being multiplied by everything else. So the absolute value of negative 1 is 1, so they disappear. Okay guys, the negative 1s disappear because when the absolute value, they become 1. So here guys, you have root n plus 1, right, over n plus 2, times n plus 1 over root n. To make it easier to find the limit, guys, let me put root n plus 1 over root n, I'm just rearranging, n plus 1 over n plus 2. Okay? Remember guys, limit of a product is product of their limits. What's the limit of that? They both have roots, so that's going to be 1. And what's the limit of that? That's also going to be 1. Overall limit is 1. So the ratio test is inconclusive. So there are times when the ratio test will fail. So you have to look at a different test. What is a good test on this? Is this a geometric series? No. Is this a p-series? No. Could we write it as a telescoping series? No. Can we do a direct comparison or limit comparison? Well, that might be a little tricky to construct because you have negative 1 to the n. Guys, the negative 1 to the power n tells you it's an alternating series. So ratio test fails, so you have to try alternating series test. Okay? You don't have to do it here. I just wanted to show you that the ratio test fails here. Okay, ratio test fails when the limit that you're trying to compute is exactly equal to 1. Alright, it's time for us to have a look at the next test, that is the root test. Okay? Just as easy as the ratio test, guys. So the series converges absolutely. if the limit as n goes to infinity of the nth root of an is less than 1. Okay, this is in fact shorter than the ratio test. For the ratio test you have to deal with a subscript n plus 1, right? But here you don't have to deal with that. All you have to do is take the limit as n goes to infinity of the nth root of absolute value of an. If that's less than 1, the series converges absolutely. The series diverges if the limit as n goes to infinity of the nth root of absolute value of an is bigger than 1, or if that limit is equal to infinity. The root test is inconclusive, guys, just like the ratio test when the limit turns out to be exactly equal to 1. Okay, those are the 3 conditions that you need to know, but you do not have to memorize them. Those 3 conditions will be given to you on the test. Alright guys, using the root test, okay, determine the convergence or divergence of this series. Now, what tells you that the root test is the best one on this? The numerator has exponent in terms of n, the denominator has exponent in terms of n. When you take the nth root, those exponents disappear, those n's disappear. Alright, so let's go ahead and find the limit as n goes to infinity of the nth root of the absolute value of an, which is e to the 2n over n to the n. So limit as n goes to infinity of the nth root of, see here guys, the absolute values are redundant here because e to the 2n is always positive, and because n is a positive number, n to the n is always positive, so I'll drop the absolute value signs. So now take care of the root. Limit as n goes to infinity of, what do you get when you take the nth root of e to the n? The n and n cancel, so you get e squared. What do you get when you take the nth root of n to the n? N and n cancel, so you get the base n. Okay, e squared is a constant. It's a fixed number. It's a constant. Constant divided by n. But when n goes to infinity, the denominator gets very large, so this limit is going to be 0, that is less than 1. So we will say the original series, e to the power 2n over n to the power n, converges absolutely by the root test. You see how easy and short that was? Right? Now, let's have a look at the exercises. Use the ratio test to determine the convergence or divergence of this series. See guys, you can, in some cases, you can apply more than one test on a series. Okay? In this case, guys, you are asked to apply the ratio test. But look at the series carefully. What other test can be applied on this series? Don't you think it's a geometric series? So you can apply the geometric series test to arrive at the same conclusion. Now we all know how geometric series works. Let's go get some practice with ratio test. So for which our an is 1 over 5 to the power n, an plus 1 is 1 over 5 to the power n plus 1. We want to find the limit as n goes to infinity of the absolute value of an plus 1 over an. That is limit as n goes to infinity of 1 over 5 to the power n plus 1, an plus 1 over an, which is 5 to the n over 1. Right, when you're dividing by a fraction, you multiply by its reciprocal. So now what do you have? When you flip it, okay, you get 5 to the n over 1. Now, where do you see an extra 5? You see an extra 5 in the denominator. So it's going to be 1/5. Absolute value of 1/5 is 1/5. What is the limit as n goes to infinity? There's no n, so this stays as 1/5, which is less than 1. So what we can say is the series 1 over 5 to the n converges absolutely by the ratio test. Okay, have a look at the next problem. You're applying ratio test on this also. So guys, what do we need? We want the limit, right? A limit as n goes to infinity of an plus 1. See whether you can do this mentally. What is an plus 1? That's going to be n plus 1 factorial over 3 to the power n plus 1 divided by an, that's same as multiplying by 3 to the n over n factorial. Okay, so limit as n goes to infinity of, look, you have to always write the larger factorial using the smaller factorial. This is going to be n factorial times n plus 1, right? Then you have 3 to the n there, 3 to the n plus 1 here, you have n factorial here. Let's simplify them all. What's going to get cancelled, guys? N factorial cancels this n factorial. You will have n plus 1. And do you also see that you have an extra 3 in the denominator? Okay, the denominator exponent on 3 is larger than the numerator exponent. And of course, guys, if you take the limit of that, that's going to be infinity, which is bigger than 1. So go to the original series, sigma n equals 0 to infinity. N factorial over 3 to the n diverges by the ratio test. Got it? Alright. Now, how do you determine convergence or divergence of the next one? Alright, let's do the ratio test. So for that, we need the limit as n goes to infinity of an plus 1, guys. What is that? Replace that n by n plus 1. 6/5, replace the exponent by n plus 1. Divided by an. So guys, flip it. 6/5 to the n flipped is 5/6 to the n. The numerator n comes down, right? And then that becomes 1 over n. Got it, everyone? Okay, so what did I do? Okay, an plus 1, I replace that by n plus 1, that by n plus 1. You're dividing by that, so 6/5 to the power n flipped is 5/6 to the power n. And then this n flipped is 1 over n. So what do we have? That's going to be limit as n goes to infinity of, any idea how to simplify this? Okay, n plus 1 over n, let me write that down. What about these numbers, guys? You have 6 to the power n plus 1, you have 6 to the power n. You have an extra 6 in the numerator. You have 5 to the power n plus 1. This is 5 to the n. You have an extra 5 in the denominator. Okay. Now if you take the limit, that's going to be 1, and the limit of a constant is the constant itself. Overall, the limit is 6/5, which is bigger than 1. So we will go ahead and write the original series. Please name it. This is the original series, and that diverges by the ratio test. Right? Okay. Determine the convergence or divergence of this one by the ratio test. Let's find the limit as n goes to infinity of, what's an plus 1? N plus 1 cubed over 3 to the power n plus 1. Flip it, 3 to the n over n cubed. So an plus 1 divided by an, in other words. Okay, let's rewrite it in such a way that makes finding the limit easier. This is n plus 1 cubed. I'll move the n cubed and put it down here. Where do we have extra 3? We have an extra 3 in the denominator, so that becomes times 1/3. Then of course you have to find the limit, yeah? What is the limit of a cubic function divided by a cubic function? It's the coefficients of their highest powers matter. If you expanded it, it's going to be n cubed plus a whole bunch of other terms. The coefficient of n cubed is 1, the coefficient of n cubed is 1, that limit is going to be 1, multiplied by a third, that's 1/3. So the overall limit is less than 1. So what's your conclusion? The original series converges absolutely by the ratio test. Okay? Next question. Can you determine the convergence or divergence of this by the ratio test? Find the limit as n goes to infinity of an plus 1 divided by an. What's an plus 1? Negative 1 to the n plus 1, 2 to the n plus 1 over n plus 1 factorial divided by an. Flip it, n factorial over negative 1 to the n, 2 to the n. Okay, so what do we have? Let's rewrite the larger factorial using the smaller factorial. So let's rewrite n plus 1 factorial using the smaller one. That's the n factorial. N factorial times n plus 1. Got it? Okay. Now go ahead and cancel whatever you can. N factorials get cancelled out. This will be limit as n goes to infinity of you have a negative 1 here and you have an extra negative 1 here. So when absolute value, that's positive. Okay? You have 2 to the n here, you have 2 to the n plus 1 here. So you have an extra 2 in the numerator and n plus 1 in the denominator. Absolute value signs are redundant, guys. You can keep them on or leave them out. The limit of that is 0, which is less than 1. So we are going to say sigma n equals 0 to infinity. I am rewriting the original series. This one converges absolutely by the ratio test. Got it? All right. Determine the convergence or divergence of this series, guys. Okay? Let's do the ratio test. Limit as n goes to infinity of e to the power n plus 1 over n plus 1 factorial. N plus 1 divided by an. Flip it and multiply. That's going to be limit as n goes to infinity. E to the power n plus 1. I'm going to rewrite the larger factorial using the smaller factorial. So n plus 1 factorial is n factorial times n plus 1. Okay, so limit as n goes to infinity. Okay, when you rewrite, guys, they'll get cancelled. So I'll have an n plus 1 in the denominator. And I'll have an extra e in the numerator. Don't think so? Because this is e to the power n plus 1. You have an extra e in the numerator. This is e to the n. So if you take the limit of this, e is a number. N plus 1 goes to infinity. E over infinity is 0, which is less than 1. So the original series, e to the n over n factorial, converges absolutely by the ratio test. Does it make sense? Good. What about the next test? N factorial over n to the n. That is our nth term. We are going to apply the ratio test to determine convergence or divergence. Find the limit as n goes to infinity of an plus 1. Go ahead and replace n by n plus 1 divided by an. Flip it and multiply. So limit as n goes to infinity of n plus 1 factorial is n factorial times n plus 1. This is n to the n. Here n plus 1 to the power n plus 1. And this is n factorial. So guys, what I did in the previous step was just rewriting n plus 1 factorial. They cancel. Now, we've seen something similar to this before. I have n to the n in the numerator. Notice that I have a lot more n plus 1s in the denominator in terms of factors. This is n plus 1 to the power 1. This is n plus 1 to the power n plus 1. When you cancel, that's going to be n plus 1 to the power n in the denominator. Does this look familiar to you? Limit as n goes to infinity. N's are positive, absolute value signs are redundant. Let me rewrite it like that. Okay guys, this is not the first time we are seeing this. See guys, earlier when I had n plus 1 over n raised to the power n, the limit as n goes to infinity was e. But now this is the reciprocal raised to the power n, so the limit is going to be 1 over e, which is less than 1. Okay, so the series, what's the name of the series? The series sigma n equals 1 to infinity n factorial over n to the n converges absolutely by the ratio test. Again guys, if you're not sure about where that 1 over e came from guys, go to section 8.8, look at L'Hopital's rule. Okay, we found the limit as n goes to infinity of n plus 1 over n raised to the power n. That limit was e. Now it's the reciprocal raised to the power n, so that limit is 1 over e.